Could you use the microphone, please?
Sorry.
Is that working now?
Hello.
Yes, that works. Thank you.
Maybe you need to pin on me, something like that.
No, it was just the sound on the computer.
Okay. Okay. We talk about temporal spatial mixing for spin systems, but from time to time we also talk about Zoom. Right. So we have to adapt to the new advances of technology. Anyways, so yeah, the talk, I'm Charis. So, and the talk is about temporal and spatial mixing for spin systems. So the term spin systems comes from physics. In reality, what I'm going to talk about is about distributions on combinatorial structures. And these are mostly specified with respect to some graph G, right? Think about independent sets, graph matchings, graph colorings, right? So these distributions have the name, come with the name Gibbs distributions for some historical reasons. And in this talk, like I will focus on the so-called Ising model and the hard code model, right? So what these distributions are, so already Will give an excellent introduction. So given some graph G, the Ising model is a distribution over plus minus assignments to the vertices of the graph. We have two parameters, beta and lambda. Beta, I call it inverse temperature. Lambda is the external field. This comes from physics, of course. And the Ising model specifies that the configuration sigma, assignment of plus minus to the vertices of the graph, gets some probability measure mu sigma, which is proportional to beta, the inverse temperature, rise to the number of monochromatic edges in sigma. Monochromatic edge is an edge with plus plus or minus minus, right? Beta to the monochromatic numbers times the field lambda rise to the number of vertices which have assignment plus other sigma, right? So it's slightly different than what Will said, but it's essentially the same thing. So we'll put these betas in the exponent. And of course, in order to make this a probability measure, we have to normalize, and we basically need to divide with a partition function. This is quantity z, right? And this is what is, we sum over all these configurations here and this weight, right? And also in this talk, partition function is a very important concept, right? So what is a hardcore model? We have again a graph G. Hardcore model is a distribution over the independent sets, right? The independent set is a subset of vertices that does not span edges. We have this parameter lambda, which in my talk I call it fugacity. And every dependent set sigma is assigned probability measure mu sigma, which is fugacity rise to the size of the dependent set, and we divide with partition function, right? So what we really will focus in this talk is compute the partition function, right? So let's see exactly what I mean by that. So for most of my talk, I'm going to focus on the hardcore model, but most of the things apply for the Ising too, right? So we are given a graph G, some fugacity lambda. We want to compute efficiently the partition function, right? ZG of lambda, which is this nice sum here. And by efficiently, I mean a time which have an algorithm which runs in number of steps, which is polynomial in the size of the graph, right? The number of vertices, right? So if you see this sum here, so you immediately realize that for general graph G, the number of summations, the number of terms here is exponentially large in the size of graph, right? So we expect to have a lot of independent sets. So there is no trivial way of actually computing efficiently this quantity here. And also it turns out that this problem is computationally hard. It's a classical SRP complete problem. So we are going to focus on approximation algorithms there. So is there any questions so far? No questions? Okay. So before getting started with algorithms, so let's think a bit about how we can count. So how we can estimate the partition function, right? And let's use a hardcore model again. Okay, so basically we have a graph G, lambda, and then someone tells you, okay, we have this configuration X, a dependent set chosen according to the hardcore model, right? Then if you also know what is the probability of X being empty, right? The empty set is an independent set of G, right? So if you told me what is the probability for X to be the empty set, then trivially you can show that, you can argue that the partition function you are looking for is 1 over this probability. Nothing more than that. Right? And then you say, okay, you do something which is also very simple. So probability of X being empty is like some basic probability fact, nothing more than that, is equal to, so you order the vertices perhaps in your favorite order, right? And then you say, okay, I have this product I from 1 up to n, and this probability Vi being in the outside the dependent set, if we choose X, conditional that all the vertices Vj prior to I, Vj for 1 up to I minus 1, are outside the dependent set already. Right? So this quantity here is what we usually call a Gibbs marginal. Right? It's a marginal for vertex Vi. And what these slides show us is that basically estimating partition function reduces basically to estimating Gibbs marginals. Nothing more than that. Right? So I told you about spin systems and counting, but at the end, what I'm going to talk about is estimating Gibbs marginals. Right? Okay, so how do we do approximate counting? So basically there are two approaches, like everything in when it gets to algorithms. So there is a deterministic way and a randomized way, right? So in the deterministic way, basically we compute numerical estimation of the Gibbs marginal, right? We do calculation. For the randomized version, we use approximate samples from the Gibbs distribution, and basically we estimate the marginal from the empirical distribution, right? So what is the best from both worlds? What's the strongest algorithm we might have? So for deterministic ones, we have what we call FPTAS, which stands for full polynomial time approximation scheme. Doesn't say much, of course. For randomized, we have full polynomial time randomized approximation scheme, or FPRAS. What they mean, an FPTAS returns an estimation z hat of the partition function, which is within a factor 1 plus minus epsilon in time, which is polynomial in the size of the graph, and 1 over epsilon. For the randomized algorithm, we have a probabilistic approximation guarantees, right? And then an FPRAS returns an estimation z hat of the partition function, which is within 1 plus minus epsilon factor from the actual value, with probability larger than 1 minus delta in time, which is polynomial in the size of the graph n, 1 over epsilon, and log of 1 over delta. Right? So yeah, we mostly care about the randomized version, but somehow the discussion is motivated by better motivated if we start discussing a bit about the deterministic approach, which is quite interesting actually. Okay, so we have a graph G, lambda, and we want to numerically estimate, say, for some vertex W, the probability of being occupied in the hardcore model. So how can you numerically do this? So basically what you need to do is you need to find a way to organize your calculations in a way that somehow help you to estimate this marginal. And we have this celebrated algorithm back from 2006 by Dorwitz that show us how to do it, right? And it uses a topological construction. It relies on topological construction called tree of self-avoiding walks. So what is a tree of self-avoiding walks? So, okay, so we go to the graph G and we focus for the walks V0 up to VR, where R can be from 0 up to N, right? These walks need to start from vertex W. The W vertex we need to estimate, whose marginal we need to estimate, right? And these walks can be either self-avoiding, so meaning that VR and up to V0 up to VW, no vertex repeats itself, right? There are a sequence of adjacent vertices, no vertex repeats. Or we can have V naught up to Vn minus 1 being a self-avoiding walk, and we can have VR some vertex we already have seen here, right? So for each of these walks, the construction TSO has a vertex. So it's a tree, and the vertex set correspond to each one of these walks here, right? So what is the edge set for this tree? So two vertices in TSO are adjacent if the corresponding walks are adjacent, meaning one walk extends the other. Okay, I think it's best to just give you one example. So here is the graph G, supposedly, and we want to create TSO starting from A. So this is the tree we get, right? So how we get this tree? Let's see some examples. So just the vertex A is a self-avoiding walk of length 0, right? So there should be a vertex for this thing here. Actually, this is the vertex here, right? It's the root of the tree, actually. And I call this vertex a copy of vertex A in the tree. Okay, let's see another path. So AB, right? So this is also a self-avoiding walk, right? So there should be a vertex for this one too. And actually, this is the vertex that corresponds to this path here. And I call this vertex a copy of vertex B, right? And since this path, this self-avoiding walk extends this one here, there should be an edge between these two vertices, right? Let's see another example. So we have this self-avoiding path A, B, E, right? So for this one, there should be an edge. This is the vertex, sorry, this is a vertex E, a copy of vertex E. And of course, as we saw before, since this one extends this self-avoiding walk, there should be, sorry, this edge here, right? And then we can also consider this self-avoiding walk, but I would like to mention this path here, right? So the path A, B, E, D, A. So this is not exactly self-avoiding because vertex A repeats, but we allow these paths, right? And these paths have their own vertices, right? For this path, we have this vertex here, the copy of A, right? Why? Because it's just the last vertex that repeats, right? And the same way we create the whole tree, right? Any questions here? Yes. 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 So it's like a lollipop at the end, or either self-avoiding or something like a lollipop or a cycle, but nothing more than that. Okay. Okay. Now, having this, so sorry, I changed a bit the name of the vertices just for the sake of making things a bit more interesting. Right, so we have this graph C, and suppose that we want to compute the marginal vertex C, right? And we create this tree of self-avoiding walks. If from the hardcore model on this graph here, we create we introduce a hardcore model for TSO, starting from C, right? Which means essentially it's just a distribution with the same fugacity, right? But apart from this simple definition, we introduce some configuration to certain vertices in the graph, right? And what is this configuration? Basically, for the leaf, we look the leaves in the tree, and if the leaf, the name of the vertex appears as we go up to the root, then this means that this leaf should have a fixed configuration. And how do we fix the configuration? So we initially have, we assume some arbitrarily an ordering for the vertices. In the specific case, we may assume the alphabetical ordering. And then if the parent of the leaf comes later in this ordering, then the leaf is set unoccupied, right? So here we have D, so D comes after C. So this C here, because it repeats, should get a configuration, fixed configuration, unoccupied, right? If you go here though, we have C again, right? So C here, C over there. So this should have a configuration, and the parent is earlier in the order, alphabetical order, right? It's B. So this leaf should be occupied, right? And with this very simple rule, we introduce a distribution for hardcore model distribution for this tree. Okay, now what happens? So let's recall what we've been trying to do right here, right? So we have this graph here, hardcore model on this graph, and we want to find the probability for C to be unoccupied. So basically, with this construction, White showed that the marginal here at the graph at vertex C is exactly the same as the marginal at the root of this tree here, right? And so, of course, this means that the probability of being occupied here is the same as this one here, but somehow this is great news, right? Algorithmically. Why? Basically, because now you can estimate the marginal, any marginal you'd like for the root by using dynamic programming, right? So actually, we typically don't try to estimate the probability of the root being unoccupied. We usually use the equivalently look the ratio of marginals at the root, right? The ratio for the marginal at the root being occupied over the marginal at the root being unoccupied, right? We focus on this ratio. And actually, we can actually show that this quantity has this nice recursive relation for the hardcore model, right? So this is ratios for the subtree that hanging from the ith subtree of the root, right? And using this equation, you can set up your dynamic program. Any questions here? Yes. Yes. No. Actually, it's for any two-spin model, and it's just actually the whole derivation is some simple telescopic trick. Yeah, it goes like it's a geniusly simple thing. Yeah, things get a bit more complicated. So, for example, if you have colorings, then for triangle-free graphs, you can do something like that. But I'm not sure for general. Maybe we'll. There is also for general. Yes. Yes. It's like very difficult to analyze. Yes, but okay, it's for general graph. So multi-spins also. Yes, and it does not. So what you're really doing here is you embed in each subtree some different measure, which on whole it looks like a hardcore model on the tree. So when you try to do this embedding for the colorings, somehow you have to start thinking different graphs. So it's a bit more dirty anyways. So but for two spins, it's as simple as that. Also for Ising model for matchings. Okay, so we have this nice construction, we have this nice reduction, right? We can compute our marginals with dynamic programming. So where's the approximate counting coming from now? Okay, so the problem is that the number of steps we need to compute this ratio at the root is big O for the number of vertices of the tree. And the tree can be huge, can be as large as exponentially larger than the graph G, right? Otherwise, we solve some NP-complete problem in polynomial type, right? So this construction gives us some nice way of organizing computation, but does not give us any aids with regards to how fast we can actually compute marginals, right? So, okay, now we start talking about approximate counting. So how can we alleviate this issue with exponential time computation? So as we do also outside computer science, we can just prune the tree, right? So we go at some level L and we just cut it, right? And instead of starting the recursions from this bottom level, we start the recursion from level L, so that the computations we need for the marginal at C is polynomial time, right? And the initial condition for the recursion is arbitrary. We don't really have a way to assume that we know something about this level, the ratios at this level of the tree. Right? Is it clear what we're doing? Okay. Now, of course, the question is, okay, how well can we approximate now the marginal? Because now we talk about, in principle, this should be the same marginal, right? We start with arbitrary configuration. So in principle, it should be something different. So how different is this thing from what we actually want to estimate? Right? And this brings us to talking about spatial mixing for Gibbs distribution. So it's more or less what also Will spent a lot of time discussing, and I'm thanking it very much for this. So we have this basic notion of weak spatial mixing, right? So what is a weak spatial mixing? Not only for hardcore model now, but also for general Gibbs distribution. So for us, of course, we talk about algorithms. It's we always have finite graphs, right? So we focus only on finite graphs. So we say that the Gibbs distribution mu exhibits weak spatial mixing on a finite graph G with decay rate Z, if and only if for every vertex V and for every subset of vertices L and for every two assignments theta and tau at this set L, we have this thing here. Yeah, let me explain what we have here with some picture. So we have this, supposing it's this graph here, right? So we have this vertex V, and we have this area with the waves is the set lambda. And this set lambda we consider two different assignments, eta and tau. Each assignment specifies a different marginal at vertex V, right? So we have this distribution and this distribution, this for eta and this for tau. Now we want to compare these two marginals at V, right? In terms of total variation distance. This is half the L1 distance of the distribution of the marginals, right? And we have this weak spatial mixing with decay rate Z if this difference is at most Z of the distance of V from lambda, right? So this is Z of R, because I denote this distance R, right? So this means that as R gets bigger and bigger, somehow this distance becomes smaller, right? The L1 distance. Is clear what happens here? And typically we would like to have z of x something like e to the minus x, right? The rate should be, we'd like to have exponentially, to drop exponentially fast with x. Any questions here? Yes? Yes, actually, yes. So this corresponds exactly to what it's great when you get these comments and it's the next slide. Great. So this corresponds exactly to the three uniqueness Will was discussing a couple of hours ago, right? So weak spatial mixing implies is equivalent to three uniqueness, right? Of course, we now focus also on the decay rate, and just remind you from Will mention this, that we have this uniqueness non-uniqueness transition for the delta regular tree, and this corresponds to the critical value lambda critical of delta, which is this quantity here, right? So when lambda is smaller than this quantity, we are in the uniqueness region, and when lambda is bigger, we have this non-uniqueness region, and all this interesting stuff going on, which we had before, right? But for our algorithm, we need something stronger than that, actually. We need strong spatial mixing, right? So what is strong spatial mixing with rate Z? So we have the similar setting as before, right? So we have vertex V, a set lambda around it, right? We put two configurations, eta and tau at lambda, right? And then we're going to compare the marginals at V that are used by these two configurations at lambda, right? And we compare them again in terms of total variation distance, but we say that the Gibbs distribution mu exhibits strong spatial mixing with decay rate Z when the total variation distance is at most Z, not from the distance of V from the set lambda, but the distance of V from the subset of lambda where the two configurations are different, right? So it could be, for example, that lambda is extensive set, right? And there are vertices in lambda that are close to V, right? But the configuration we consider eta and tau are disagreeing very far from V. Then this distance should be small because the disagreement is far, right? It might be lambda is close to V, but since the disagreement is far, this should be small. Make sense? Any questions? Okay, so this is what we really need for our algorithm. Okay, so if you have some questions about SSM, let me tell you that for the conjecture is somehow that SSM coincides with WSM, with strong spatial mixing coincides with weak spatial mixing for trees, right? It means that these two phenomena somehow appear for the same region of the parameters of the Gibbs distribution. We know that this is true for two spin distributions like the hardcore model or the Ising model. For multi-spin distributions, when we have more than plus minus and plus or minus, but we have more spins, then it's still open. We are looking into it. Okay. So essentially, so what I want to say here that even though for technical reasons we assume that there is strong spatial mixing in the Gibbs distribution, uniqueness that Will was talking about is essentially what characterizes the measure. Right, and then what do we have? Let's see what is result for the hardcore model, but also this applies to Ising model and all kinds of Gibbs distribution. So okay, we have a graph G. Let me parse the theorem for you. So we have a graph G of maximum degree delta. We have lambda in the uniqueness region for the delta regular tree, right? Then this construction with the TSO and the estimation of with pruning and so on returns an estimation z hat of the partition function we want to estimate, which is within a factor 1 plus minus epsilon in time, which is big O of n over e, this e here, rise to some constant c, which depends on how far we are from the threshold, uniqueness threshold, times log of the maximum degree. Right, and okay, we have some bad dependence on the maximum degree. We have this log delta in the exponent, but we cannot really do anything more than that. Right, so if you want to get something faster, you need to start talking about randomized algorithm, right? And but before going there, let's make some general observations. So, as Will nicely discussed in his talk, when we don't have SSM, when we don't have uniqueness, the problem becomes hard, right? And I just wanted to mention that this is the hardness of we have here is a hardness of approximation thing, right? Yes, and this is I agree with Will that somehow it's really beautiful that we have this phase transition that signifies the transition from efficient algorithms to hardness. It's a really beautiful connection, right? And yeah, this this is somehow something to think also for my talk tomorrow, right? So we have this dependence here for the parameters on the maximum degree of the graph, right? So if we have a graph G of maximum degree delta, basically we need uniqueness for the delta regular tree, right? So the range of the parameters are a function of the maximum degree. So this is what we have here, right? So is there any questions so far? I'm moving too fast. Okay, so let's see the randomized version now. So how much time do we have? 10:50. Oh, okay. Oh, I was a little bit late. So approximate sampling. We want to estimate marginals by using approximate approximate samples from the Gibbs distribution, right? And what we are going to do here is we are going to use the Markov chain Monte Carlo method, right? MCMC as we call it. Particularly, we're using what we call Markov chain called Glauber Dynamics, right? So this is a discrete time Markov chain. The configuration space is the support of the distribution we want to sample from. Say hardcore model is the dependent sets. And the setup is so that the Glauber Dynamics converges to the Gibbs distribution we want to sample, right? So this requires some technical conditions called ergodicity. In most of the cases, is trivially satisfied. So Glauber Dynamics has this nice transition rule, right? So if you are at a time t-1, you are configuration x sub t-1, we get x sub t. How? We choose uniformly a random vertex from G. All vertices different than V keep the same configuration, and X, the configuration at V is updated according to the Gibbs marginal conditional what happens in the neighborhood of V. Let's see an example here. What happens with the Glauber Dynamics for the hardcore model? Suppose that we have this star graph, and we want to update vertex V, right? So if none of the rays 1 up to 8 is occupied, is in the dependent set at time t plus 1, V gets into the dependent set, becomes occupied with probability lambda over 1 plus lambda, right? Lambda is a fugacity. Otherwise, for example, if 6 is in the dependent set, then we cannot put V into the dependent set. So V becomes occupied with probability 0 apparently. Right? So what is the idea here? So basically we have an algorithm that simulates the Markov chain for sufficiently large number of steps and then outputs the configuration, right? So the more we run the chain, the larger the number of steps T we simulate the chain, the closer XT gets to the equilibrium distribution, right? So in that respect, our focus is on how fast the chain mixes, right? The mixing rate of Glauber Dynamics. And as a measure for the mixing rate, we typically use the mixing time. What is the mixing time? It's basically the minimum number of steps T, so that whatever the initial configuration of the chain, after T steps, we are the configuration of the chain is at L total variation distance within total variation with 1/4 total variation distance from the equilibrium distribution. Right? And basically what we need to have here in this setting is that the mixing time should be some small polynomial of the size of the graph, maybe n log n or n squared, something like that. Right? So what do we know? So we have this general, very amazing result, I would say. So choose one of the two distributions I mentioned before, like hardcore model or the Ising model, right? And set the parameters somewhere in the region where we have the uniqueness for the delta tree, right? And then take the Glauber dynamics for this distribution on the graph G with maximum degree delta. Then the mixing time is optimal. It's n big O of n log n. I think we cannot hope asymptotically to get anything better than that. Right? And this series of results comes, this result comes from a series of results by Anari, this one's here, basically. All right, and these rely on what we call the spectral independence method. Right? So this uses ideas from techniques from high dimensional expanders to prove these amazing results. So let me tell you what is the basic ideas here. So spectral independence. So the main object there is what we call the pairwise influence matrix, right? So we have a Gibbs distribution mu, and we define this matrix I sub G, which is, this matrix is indexed by the vertices of the graph here, right? And the entry WU is this quantity here. So let me tell you here what happened. So basically, we have the graph here G, right? And we look the marginal at vertex V. As we vary this vertex W, the configuration from plus to minus, and see how different is the marginal here. So this is the entry WV for the influence matrix, right? This is what this total variation distance stands for, right? And also you can actually assume consider the influence matrix for when you have you impose configurations, you fix boundaries and your measure, right? Have again a pairwise influence matrix. Okay, so basically, having defined this pairwise influence matrix, we care about what is the spectrum of this matrix. Particularly, we care about what is the maximum eigenvalue, right? So for some number eta, we say that the measure mu is eta spectrally dependent if whatever conditioning we put into the measure for vertex set lambda and configuration tau on this there, the corresponding pairwise influence matrix has spectral radius, which means also maximum eigenvalue, which is at most 1 plus eta. Right? And then there is this celebrated result by Anari and Tal that says that if you have some fixed number eta, right, and mu, your Gibbs distribution is eta spectrally dependent, then the Glauber dynamics has spectral gap, which is given by this quantity here, which implies that your mixing time is some big polynomial in n of n, right? So this is something like n to the 1 over eta. But perhaps the state of the art is this theorem here, which says that if m is eta spectral dependent for some fixed number eta, then Glauber Dynamics exhibits mixing time with this big O of n log n. So this has improved to optimum, asymptotically optimum, right? So of course this result is not precise enough, but as it is here, somehow it applies almost directly for the hardcore model and the Ising model, right? And also applies for the bounded degree graphs. Yes.
So the point is, like, you really have like a sequence of lines of things where if data all
Yes. You're allowed to play with the L lambda. You're allowed to put some configurations there so that perhaps increase the maximum eigenvalue or the spectral radius of this matrix. Actually, this matrix is quite nice. So maximum eigenvalue is the same as the spectral radius. Okay, so yeah, basically the idea now is what SSM has to do with all this stuff with spectral dependence, right? And basically, we're going to briefly show you how SSM implies spectral dependence, meaning that the spectral radius of the influence matrix is constant, right? And actually, we won't move away from these shows, right? So how do we bound the norm, the spectral radius of the influence matrix? Basically, we use matrix norms, right? So, but classically, we use the infinity norm, right? Infinity norm for the matrix is basically, we look the absolute row sums and we pick the largest one, right? So, okay. So we have also this tree construction, like this tree reduction we saw before for the deterministic algorithms, right? If you remember, we have this vertex C, right? When we create this T-so there, we put some boundary conditions and we have this nice relation with the marginal at C, right? So for now, what we do is for this tree here, we can actually, for this measure here, for this hardcore model here, we can consider the influence matrix also, right? No one prevents us from defining the influence matrix here. And there is this amazing relation that somehow you can argue about the entries of this matrix here for the graph G by utilizing the influence matrix for the tree, right? And it says the following, basically. So the influence of vertex I to the vertex E, that we play with I, put plus minus at A, and we see how the marginal at E changes, can be given by going here in the tree and taking the sum of influences of A to the copies of vertex E, right? So we change the configuration at the root now, the tree, from plus minus to plus to minus, and we see how this for each one of the copies of E of vertex E, the marginal changes, and we sum all over these changes, right? This is somehow analogous to the marginal we've been looking for the deterministic algorithms. And then, so with the infinity norm, basically what we need for the graph is to compute the influence of A to all the vertices in the graph, right? And this, of course, for the tree, this is reduced to the tree by just summing the influence of A to all the vertices in the tree here, right? Okay, so how can we do this? We get again to the ratios at the marginal, at the root, right? The ratio of marginals at the root. Now we do some small transformation. We don't really look this the recursion we had before, but we actually we look the log ratio, right, as we call it. We have this function h sub d, which expresses the log of the ratio at the root as a function of the log of the ratios of the subtree, right? And then basically you can argue that the total inference of a vertex W to all the vertices in the graph G here, right, is given by this expression. We take the gradient of H, right, here, inner product with the influence for each subtree, for the root of each subtree to the vertices in this subtree, right? For the subtree I, the root, what is the influence the root has to the rest of the vertices, right? So we have this vector and we take the inner product, right? And we evaluate the gradient at this point here, right? Anyway, so I'm speeding a bit up. So this equation essentially reduces to arguing that at its vertex here we have a value, right? For this vertex D, we have this value h of Rd, which is some partial derivative of this function h, right? Which refers to the subtree, right? And then what we want to do with these quantities is basically you just apply Hölderlin inequality, something like that here, right? And your focus now, right, when you do this is you want to bound some norm of the gradient of this function h, right? And particularly what you want to do is find some norm for this gradient that somehow is smaller than the growth rate of the tree, right? And the worst case, this TSO you have is a delta regular tree, right? And having a gradient that norm for the gradient that is gives you something like 1 over delta or delta minus 1 is basically equivalent to requiring from your Gibbs measure on the tree to exhibit strong spatial mixing, right? So this is how we get, again, strong spatial mixing for to get rapid mixing, spectral dependence and rapid mixing. Okay, so is there any questions here? I rushed a bit here a bit. Okay, so conclusion. So we saw some connections between spatial mixing and temporal mixing for spin systems. So these techniques apply mostly for two-spin Gibbs distributions like Ising model and the hardcore model. So with the hardness we have for, I talk about hardness for deterministic, but of course this applies also for Markov chains, right? So in worst case, non-uniqueness implies slow mixing, right? And so the question is, can we do something better than what this distinction implies? Like, can we do something without solving some NP-complete problem? Can we somehow do something better than what this picture here implies? And the answer is yes, and this is going to talk about tomorrow. So this is it. So any questions? Okay. Okay.